Hello, good morning everyone. My name is K.VIDHYA SAGAR. Now we are going to discuss about the preparation of oxygen. Okay. Oxygen gas we can prepare by the oxygen gas. We can prepare by the from 2KClO3 decomposition in the presence of MnO2, then forms KClO3. 2 moles of KClO3, MnO2, then formation of 2KCl plus 3O2 will be formed. Okay. So here another one method, preparation of oxygen. Yeah, that is 2 moles of K-4 potassium permanganate undergoes a decomposition. The formation of K2MnO4 potassium manganate as well as MnO2 plus oxygen gas is liberated. Decomposition of potassium permanganate also. And the next preparation, decomposition of the some metals. Decomposition of some metals also give the oxygen. Okay. Now going to see that metals. 4 moles of Ag2O undergoes a decomposition, then formation of 2Ag, 4Ag plus O2 will be formed. Decomposition of some metals also give the oxygen. Next, Pb3O4 undergoes a decomposition, then formation of 6 PPO plus O2 will be formed. As well as PbO2 also undergoes a decomposition, then formation of O2. Thus, these are some metals are undergoes decomposition, then formation of oxygen gas. Including these, decomposition of hydrogen peroxide. Hydrogen peroxide, 2 moles of H2O2 hydrogen peroxide, which is undergoes a decomposition, then formation of 2H2O plus O2 it will be formed. O2 gas it will be liberated. Okay. And industrially they will prepare the oxygen. Now you know that in the corona second wave situation, oxygen is how much demand here. How they will prepare? Yes. Now see the preparation of oxygen industrial level by the electrolysis of water. By the electrolysis of water. Now I am going to take, see, water. Water undergoes dissociation. Yes. Then formation of H plus plus OH minus. So these ions are undergoes electrolysis. The anode and cathode. This anode, this cathode undergoes electrolysis. Okay. At anode, what happens, you know, anode has a positive charge. This anode, this cathode. At anode, oxidation takes place. At cathode, reduction takes place. At anode, what happens, you know, 4OH minus. 4OH minus undergoes electrolysis, then formation of O2 plus 2H2O will be formed. O2 plus 2H2O. If you take here 4 moles, 4H plus plus 4OH minus, here O2 plus 2H2O it will be formed. And at the cathode, 4H plus undergoes electrolysis, then formation of H2 gas, it will be liberated. H2 gas, it will be liberated. Okay, it means that by the electrolysis, okay, at anode, we are going to produce the oxygen by industrial level. Okay, right. If you want to observe the properties of oxygen, if you want to observe the properties of oxygen, it is a diatomic gas. It is a odorless gas. Odorless gas. Okay, which is soluble in water. Soluble in water. The soluble oxygen, how much amount of oxygen which is soluble in water, that is useful for the respiration for the aquatic animals. Aquatic animals. Aquatic animals. And you know that O2 oxygen is a paramagnetic substance. O2 is a paramagnetic substances. Okay. Now see here, this O2 is combined with many metals as well as non-metals. This O2 is combined with many metals as well as non-metals. Now we are going to observe here, which is combined with, okay, calcium, which is combined with P4, and which is combined with aluminium, which is combined with zinc sulfide, which is combined with sulfur dioxide, which is combined with carbon, okay, which is combined with many metals and non-metals also. The calcium is combined with oxygen, then formation of calcium oxide. P4 is the reaction with combined with oxygen, then formation of P4O10. And aluminium is combined with oxygen, then formation of Al2O3. 4Al plus 3O2. Zinc oxygen also combined with oxygen, then formation of ZnO plus SO2, 2 moles, 2 moles, 2 moles. And sulfur dioxide also is combined with oxygen, then formation of sulfur dioxide, then the catalyst is at B2O5. And the carbon also is combined with oxygen, then formation of carbon dioxide. It means that this oxygen is combined with many metals as well as non-metals, then formation of oxides. Okay, I will see here. Sir, what are the uses of oxygen? Now we are going to discuss about the uses of oxygen. Uses of oxygen. Okay, in the uses of oxygen, oxygen which is useful for, you know, the respiration for all type of living organisms, including marine life organisms. Okay, nowadays which is producing for the hospitals, for the oxygen is required for the hospital patients, and majorly oxygen which is used in oxyacetylene welding, which is used in oxyacetylene welding, right? I will see here This oxygen, liquid oxygen, is used in rocket fuel. Liquid oxygen which is used in rocket fuel, and which is combined with the hydrogen, then produce tremendous amount of heat. When liquid oxygen is combined with the hydrogen, then produce tremendous amount of heat is released. Okay, so these are the some uses of oxygen, right? Now we are going to discuss about the ozone. Ozone, O3, so ozone, O3 molecule. It is the least stable at the sea level. Sea level is the least stable, which is highly reactive. Okay, and you see here, this ozone is above the earth 20 kilometer upside is present, 20 kilometer upside, which is protect from UV rays and some UV rays. It is protect the earth, right? Now see, now how can we prepare the ozone? Ozone we can prepare by the oxygen. Okay, then with oxygen, which is passes through the silent electrical discharge tube. Silent electric discharge tube. Silent electrical discharge tube. Then formation of 2 moles of O3 will be formed. Then delta H is equal to plus 142 kilojoule per mole amount of heat is absorbed. 142 kilojoule per mole amount heat is absorbed. It means that this is a endothermic reaction. This is a endothermic reaction. Heat is absorbed. Okay. Sir, why you are taking silent electrical discharge? Why you are taking silent electrical discharge? It means whatever the amount of ozone is formed, that is thermally least stable. Okay, so to get the stability of ozone, we are using the silent electrical discharge. Okay, and then you see here, whatever the ozone is formed, that ozone, if it is available in the gas, if it is available in the liquid, if it is available in the solid, okay, the liquid which is a pale blue color. Okay, in the liquid, this is a dark blue color. In the solid, which is violet color. Okay, violet color it will be found. It means that violet black, look like some black color, violet black color it will be found. Okay, and you see, which is less concentration. Less concentration is a harmless, it's not harmless, but its a concentration is crossed 100 ppm above. 100 ppm above. Its concentration is crosses 100 ppm above. Okay, it is gives some problem, headache, nausea, vomiting sensation, as well as ultimately sometimes the death will be also happens. Okay, right. And you see here, Here one very, very important point you are observing. That is that formation of ozone as well as decomposition of ozone. Formation of ozone, 3 moles of O2 and this delta H is equal to plus 142 kilojoule per mole. Decomposition of ozone, so delta H is equal to highly negative. Highly negative. It means delta H is equal to negative. It means that now what I am going to explain, you see, 2 mole converting to the 3 mole. 2 mole converting to the 3 moles means entropy is always positive. Entropy is always positive. 2 mole converting to 3 moles means entropy is positive. And delta H is equal to negative. According to Gibbs energy principle, delta G is equal to delta H minus T delta S. Delta G value, delta S negative, okay, minus temperature. Delta S value positive. Now see here. Negative into positive, negative here, negative. So delta G is always negative, sir. When my delta G value negative and which it does not depend upon the temperature. It does not depend upon the temperature. You got it? So delta G value is, if temperature high or low, whatever is that, it does not depend upon the temperature. Delta G value negative. Delta G value negative means the decomposition of ozone is okay, readily takes place. It's a blast. Okay, so that's why you remember that delta G value is negative for decomposition of ozone, right? And this ozone is decomposed. Ozone is decomposed. O3 decomposed, then formation of O2 plus O. Produce nascent oxygen is produced. That's why O3 is act as a powerful oxidizing agent. O3 is act as a powerful oxidizing agent. So this O3 PBS, lead sulfide is reaction with O3, then formation of lead sulfate plus oxygen gas is liberated. Lead sulfate plus oxygen gas is liberated. As well as this O3 is reaction with O3 is reaction with iodine, then which is gone into the I2 plus, then forms 2OH minus. I'm telling that their ozone is a highly oxidizing agent. Iodine as state minus 2 to 0 oxidize the iodine itself undergoes reaction. Okay, so ozone very powerful oxidizing agent. These two reactions are very, very important to see. These two reactions. Okay, right. Now, the one more important point about the ozone layer, it is going to depletion. Depletion of ozone layer, why it is going to take place? Why? Because, okay, jet rockets release the nitrogen monoxide in atmosphere. Jet rockets release the nitrogen monoxide in the atmosphere. The nitrogen monoxide is highly reactive towards ozone. Then formation of nitrogen dioxide plus oxygen gas is liberated. So due to this reason, ozone layer is undergoing to depletion. And as well as not only jet rockets, refrigerators, and chlorofluorocarbons also damage the ozone layer. Okay, right. Now, sir, what are the uses of ozone? Now we are going to discuss about the uses. Uses of ozone. What are uses of ozone? Ozone uses. See, ozone, which is used as a disinfectant, as well as kills the microbacteria. Kills the microbacteria. Okay, and these ozone also act as a very powerful oxidizing agent. Oxidize the ivory, oils, flour, starch. So these many compounds are oxidized, means act as a bleaching agent. What is that? This is act as a bleaching agent. It bleaches the ivory, oils, flour, starch, etc. And this ozone is used to preparation of K-4. In the preparation of K-4, ozone also is act as a very powerful oxidizing agent. Very powerful oxidizing agent. What I mean, in the preparation of K-4 also, ozone is act as a very powerful oxidizing agent. Okay, these are some uses, and ozone is exhibits two resonance structures. Okay, this is the structure of ozone. Their bond length, bond angle 117 degrees. 117 degrees is present. Okay, right. Now we are going to discuss about the oxides. Oxides of sixth group elements. Now see here, generally simple oxides. Generally, oxides are two types: simple oxides as well as mixed oxides. Simple oxides as well as mixed oxides. In the simple oxides, best example CaO, Na2O, these are the simple oxides. Mixed oxide, best example Pb3O4 and Fe3O4, these are the examples of mixed oxides. In that oxides, these elements having two different oxidation states. Okay, and these are the simple oxides. These oxides are classified into the four types. How many types? Four types. Sir, what are those? One is the acidic oxides. One is acidic oxides. Another one, second one, basic oxides. Third one, amphoteric oxides. And fourth one, neutral oxides. Fourth one, neutral oxides. These total oxides are classified into four types. Sir, what are acidic oxides? See, best example I am going to take: carbon dioxide is acidic oxide. Sulfur dioxide is acidic oxide. Okay, carbon dioxide, sulfur dioxide, as well as Cl2O7 also. These all are acidic oxides. Sir, what are acidic oxides? These are the oxides. For example, I am going to take carbon dioxide. These are the oxides, reaction with water, then formation of acid. You see, carbon dioxide reaction with water, then formation of carbonic acid. What is this? Carbonic acid, it will be formed. Carbonic acid. Okay, and as well as sulfur dioxide or sulfur dioxide is reaction with water, then formation of S2SO4. Okay, if you take SO2, formation of S2SO3, sulfurous acid. Okay, so now you remember, sir, what are acidic oxides? Those are the oxides reaction with water then produce the acids. Those are oxides are said to be acidic oxides. Okay, but you know that the important point, sir, according to the general rule, all metal oxides are basic in nature, all non-metal oxides are acidic in nature. Okay, but some metal oxides are also, all metal oxides are basic in nature. All non-metal oxides are acidic in nature. Metal oxides are basic in nature. But some metal oxides are acidic in nature in the highest oxidation state. In the highest oxidation state. Now see, here manganese is a metal. MnO4. MnO4. See, this is acidic in nature. Why? Because these are having the highest oxidation state. But this metal oxide, we can't say it's a basic. It is acid. Why? Because in highest oxidation state. Not only that, even B2O5, even CrO3, these all are metal oxides. What is the general rule? All metal oxides are basic in nature. But here metal oxides are acidic in nature because these are exhibit the highest acidic nature. Highest acidic nature because highest oxidation state is there. That point to remember. Okay? Right. And the next, now we are going to discuss about the basic oxides. Basic oxides. In the basic oxides, the best example, Na2O, CaO. Sir, what are basic oxides, sir? Basic oxides means those are the oxides dissolved in the water, then produce the bases. See, sodium oxide dissolved in the water, then formation of base. Sodium hydroxide, it will be formed. Sodium hydroxide. Okay, right. So these are the basic oxides. Basic oxide, best example, Na2O, CaO, Na2O, MgO. These are the some basic oxides are present. BaO, CaO, BaO, some basic oxides. These all are reaction with water then produce. What is that? Bases. Okay. And some oxides are amphoteric in nature. It means that they are having the both acidic nature as well as basic nature. Now see. Now see, best example for amphoteric oxides. Amphoteric oxides. Best example, Al2O, SnO2, okay, tin oxide, lead oxide. See, these all are best example for amphoteric oxides. See, amphoteric oxides means these are oxides are act as a both acidic nature as well as basic nature. It means that those are going to reaction with the acids as well as base. Now going to see, we are going to discuss about the reaction. See, Al2O3, this is the amphoteric oxide. This Al2O3 is reaction with, see, here 6 moles of HCl plus 9 moles of water, then formation of 2 moles of Al, H2O, taken 6 plus 3 plus 6 Cl minus, it will be. It means that Al2O3 is reaction with acid. Okay, then formation of the hexa, hydrox, aqua, hexa, aqua, aluminium, it will be formed. Now this Al2O3 also reaction with the Al2O3 also reaction with the base. Acid reaction over, which also reaction with the base. Okay, in the presence of water, then formation of 2 moles of AlOH taken 6. AlOH taken 6. It will be formed. The oxidation state here plus 3. Okay, so this is the compound it will be formed. It means that this reaction is confirmed that aluminum is reaction with the HCl acid, aluminum is reaction with base in OH. So it's reaction with both compounds. So that's why this is the best example for amphoteric oxide. Now we are going to discuss about the neutral oxides. Now we are going to discuss about the neutral oxides. Neutral oxides. Sir, what are neutral oxides? See, best example you remember N2O, ha ha ha, it's a laughing gas, as well as NO, as well as carbon monoxide. These are the best neutral oxides of gases. All are gases. You remember, right? Okay. Now, this is the information about the oxides. Now we are going to discuss about the allotropic form of sulfurs. Allotropic form of sulfur. Allotropic form of sulfur. In the allotropic form of sulfur, which is 2 types of sulfur, alpha sulfur, okay, as well as beta sulfur. Alpha sulfur is a, which is yellow color, yellow in color, yellow rhombic sulfur. Yellow rhombic sulfur. Beta sulfur is called monoclinic sulfur. Monoclinic. So monoclinic sulfur. Okay. So these sulfur, how they are going to prepare? Okay, what is that? We'll discuss now. Alpha sulfur, we are going to prepare. Okay, that is roll sulfur. You take roll sulfur, roll sulfur. The roll sulfur you dissolve in carbon disulfide. Roll sulfur dissolved in carbon disulfide, and then evaporate the carbon disulfide. Then you get wonderful crystals of yellow rhombic sulfur or alpha sulfur. And this alpha sulfur is yellow in color. That's why it is called yellow rhombic sulfur. Okay, and this alpha sulfur not soluble, insoluble in water. Not soluble, insoluble in water, but soluble in benzene as well as alcohol as well as ether, and readily soluble in carbon disulfide. Readily soluble in carbon disulfide. Okay, and you remember this alpha sulfur stable at 369 Kelvin temperature below only. Stable at 369 Kelvin temperature below only. That point. This temperature is important. You remember 369 is a universal number. This is a Tesla number. This is a universal number. Just you remember this. Okay, right. And you see, sir, how they will prepare the beta sulfur. How they will prepare the beta sulfur. So beta sulfur they will prepare. You take the alpha sulfur in the one bowl. and heat, okay, and cool it. Heat and cool. The ball outside one layer it will be formed. Layer that is called one crust. For the crust you made two holes. For the crust you made two holes. Inside of the total liquid you poured outside. Then you open this crust. The crust inside wonderful crystals of monoclinic sulfur or beta sulfur it will be formed. Beta sulfur it will be formed. Okay, wonderful crystals of beta sulfur form inside. Okay, right. And you remember one important point: alpha sulfur to beta sulfur. Alpha sulfur to beta sulfur. 369 Kelvin temperature is a very essential effect here. 369 Kelvin temperature is a very effectively works. Means that, what is the meaning of that? 369 Kelvin temperature below alpha sulfur is exist. 369 Kelvin temperature above beta sulfur is exist. That's why this temperature is called transition temperature. Transition temperature. Transition. The last, how much transition temperature? 369, 369 Tesla number, universal number. Okay, right. And one more important point, that is alpha sulfur or beta sulfur, which is existing SEIT molecule. Which is existing SEIT molecule. SEIT molecule puckered or crown shape, which is present in crown shape. See, this is crown shape or puckered shape is present. And this SEIT molecule, after several modifications, which is going into S6 as well as S2. S6 molecule, which is cyclic chair structure, chair form, which is existing chair form. Here one sulfur, here one sulfur, here one sulfur, here one sulfur, like this. And S2 molecule, yes, for the competitive level, this is important. S2 molecule is more stable. S2 molecule is a more stable. S2 molecule having paramagnetic nature. Like O2. O2 molecule, how it is a paramagnetic nature? S2 molecule having also same paramagnetic nature. So this is the information about the allotropic form of sulfur. And tomorrow we are going to discuss about the sulfur trioxide and sulfuric acid and oxides of sulfur. Tomorrow we are going to finish 6th group elements. Okay? Thank you very much. Bye. Right there.